Okay, hello again. Today we will be solving some problems for your final exam. I have quite a bit to work on today. Namely, I have, what is it now? 9 questions, but all of them have design and synthesis in it. So hope that this will be helpful for you today. So let's start with the first question. By the way, you don't really need to take any notes because I will publish the PDF for you. Everything that I write on the board will be on the PDF. So, all right, let's start. Now we have a system, GS, 6 divided by S cubed plus 7s squared plus 6s. So that's our system. And we want to find the interval for a p-type controller using one time domain and also the frequency domain. And there's also another question. So this is basically A, this is B, and C is what is the time constant that can be added to the system? So basically how much delay can be added to the system to destabilize the system. So these are basically the questions of the first question. And by the way, during the final session, I'll be using the time domain. On the other hand, I'll use the frequency domain to compare stuff, so it is going to be parallel to each other. So, now, as usual, how do we attack the problem for time domain? We will use basically the transfer function. So for A, k gx divided by 1 plus k times gx will be our focus. Well, since I have the numerator and denominator, what I can do is I can do the following. I can say 6 times ns plus ds will be my, basically k times ns ds will be my characteristic polynomial. Therefore, I have 6k plus s cubed plus 7s squared plus 6s. That would be my characteristic polynomial. Now, you can of course use the root locus method, since this is a basic system, but I'm going to use s equals j omega. I'm going to plug this in because I'm interested in a point. Let's have this root locus here. I don't know what the poles here are, but I guess it was 6 and 1. So we have minus 1 and minus 6. So we have kind of this structure here for the root locus plot. I can interpret that because I can calculate the poles. Since one of them is S and I don't really have constant term for K0, I can see that there is 1 at the origin here, 0. And I'm interested in this point here. So let me pick another color. Where is it? There we go. So I'm interested in this and this. So we will have here j omega and minus j omega. Of course, the third pole will be somewhere here, which I don't really know. So the closed polynomial would then look like s plus p somewhere there, and then s squared plus, since I have j omega, I can also do this like this, s plus j omega times s minus j omega. Therefore, I'm looking at s plus p, and this is basically s squared plus omega squared. So that's really the thing that we should look at for the closed loop. For such a k, this system is marginally stable. Now, of course, I can use this stuff here. For example, you can use s squared equals minus omega squared and plug it in and work your way out, but the problem would be then 6s. Therefore, it's much safer to use S equals j omega, plug it in, and look what the result looks like. So basically, P omega, or j omega, characteristic form over here, 6k minus j omega cubed minus 7 omega squared and plus 6j omega defined in state. Now, since this is a complex number, I have to remind you that the real part should be equal to 0, the imaginary part should be equal to 0, because I want to satisfy this equation. It should be equal to 0 if it's the root of this polynomial in a closed loop. Therefore, I'll take the imaginary parts, so minus omega cubed plus 6 omega should be equal to 0. And we also have 6k minus 7 omega squared. So basically 6k is 7 omega squared. Now from here, I can see that this is basically omega squared minus 6 equals 0. Therefore, one of the solutions would be, let me go here, omega equals 0. And you can see that if omega is equal to 0, we have again another equation. If I plug it in, k should be equal to 0. So that's one of the solutions. And the other one is omega squared equals 6. Therefore, 7 times 6 divided by 6, k is equal to 7. So, basically these are my solutions. You can see that there will be a crossing at omega equals 0 because, let me again take another color, because on the negative root locus, I will have such a branch that will pass through the origin, therefore omega will be 0, and it exactly happens at k equals 0, which also means that we have basically, this is the open characteristic polynomial, or you can look at this, and see that we have already a pole at the origin, therefore s is already equal to 0, so we are aware of this solution already. But the interesting part here is that omega squared is 6, or square root of 6 is omega, and k is equal to 7. So if we plug in 7 here, for the closed loop, I mean here, then we end up in s cubed plus 7s squared plus 6s plus 42. So if you look up the roots, you should basically get the structure here. S squared plus 6 should be, so s squared plus 6 equals 0, should be one of the pieces here. You can maybe divide this into s squared plus 6 and then see what the third pole is, but it's not really that relevant in this case. So what is the interval? Well, basically on the negative root locus we have already k equals 0, and here we have seen that it is 7. So our stability interval would be 0 and 7. And we've worked out what the structure looks like. So for B, for the B part, let me just get rid of this part here. So for B, what do we have here? Well, we have the system itself, and normally you need the body diagram in order to use the frequency method, but it's not really that necessary if you have the transfer function itself. You can also work it out from here. So what I mean by that is the body plot gives you basically this information. You have a certain magnitude graph and a certain phase graph. But if you have this transfer function itself, if you plug in s equals j omega, then you get j omega equals 6 divided by. Now this is again j omega cubed, and then we have minus 7 omega squared and 6j omega. Now you can clearly see that this is basically a complex number, or a complex value function, because it's a function of omega, but the results will be complex numbers. And if you take the absolute value here, so let me just abbreviate like this, what you will get is you have 6, so I can leave that, because the absolute value of the whole thing is the absolute value of the numerator, denominator divided into each other. Well, basically I can therefore take 6 on its own, but we have imaginary and real parts. So if I have a plus bi or pj, a squared plus b squared square root will be my magnitude. Therefore, I can just use this part here, 6 omega minus omega cubed squared plus, and then 7 omega squared or minus 7 omega squared and the square root of that. So yeah, basically we are familiar with this because we have that on the right part. You can see that I have written basically minus omega cubed, 7 omega, 6 omega, I'm sorry. So this is basically this part here. And then there's also 7 omega squared, which is again this part here. So let us leave it like that for a moment. We also need the argument here. So r of g omega. This is also important for us because this is not needed at the moment if we are looking for a p-type controller. The first thing that we look at is basically 1 plus k. G should be equal to 0, therefore we should look for minus 180 degrees phase angle. So therefore we need the phase relation here. And we can obtain it again if you look at this complex number, complex value function. You can see that the argument of the whole thing here is basically the argument of 6 minus the argument of this part here. So, well, minus j omega cubed plus 6. So let's write this one here. 6 omega minus omega cubed j, minus 7 omega squared. The argument of that and the minus sign, and the argument of 6 is basically 0. So this is 0. And we'll use the inverse tangent here because we have the imaginary part, the real part. So a tan or tan inverse of 6 omega minus omega cubed divided into minus 7 omega squared is basically the angle or the phase angle that we get from the system. Now, we're good to go, basically. Yep. So, just here. Now we have to equate it to minus 180 degrees. So that's basically it. So, if I'm not wrong, if it's minus 180 degrees, then the tangent of that, so tan minus 180 degrees, should be equal to 6 omega minus omega cubed divided by minus 7 omega squared. So if I'm not wrong, this tangent should be equal to 0 because sine is 0 divided by cosine, which is not 0, therefore this is 0, and you will get 6 omega minus omega cubed equals 0, or in other words, we have omega 6 minus omega squared equals 0. Again, we have two possibilities. One of them is omega equals 0, the other one is basically square root of 6. Now, you can see already that we have basically the same equation here. We get the same frequencies. The only thing that is left is to plug it in into this, but since this is 1 divided by d omega, the absolute value of this, so it's basically the inverse, we flip it, we get 6 omega minus omega cubed, the square of that plus 7 omega squared divided into 6. Now obviously if you plug in omega equals 0, you get 0 for k, so that's one solution. And if you use this is 6 basically, and then there's omega squared 6, and if you use also the square root of 6, you'll get basically again the same value of 7. I don't really have to basically calculate this. You can just use your calculator and see that this is basically the case. So what we've done so far is that we have looked at the time domain version of the solution. Of course, one might argue if this is really a time domain approach, but well, we plug in a pole and look for 0. I'm plugging in this point here, so it is basically a time domain solution. But a more generic one would be to use the root locus gain condition, phase condition. But yeah, you already know how to do that, so I've skipped that part. We've seen that the frequency domain is also basically verifying the same result, gives us the same result. So this is the first part. Now we have C, therefore I have to get rid of the second part maybe. So up to this point, we have added a static gain to the system. But now, we are asked to add a delay to the system. I can also maybe get rid of this one. There we go. Now the question is the following. Let's use a delay like this, add it to the system, and have a unique feedback. So this is minus, this is plus, again we have the reference, yellow push, etc. This is a bit different than adding a static controller because up to this point we were adding a static gain at this point. But now we are adding a delay to the system. So therefore we'll look at that. So this is not really important. Yeah. So basically we have to look at the closed loop here because it's again about the stability. How much time delay can be added to the system and using unit feedback structure such that we have a stable closed loop transfer function or modular stable. So how big of a delay can we add to the system without touching its stability? That's basically the question. So in order to do that, we have to write down what the system looks like. It's 6 e to the power of minus tau s divided by s cubed 7s squared plus 6s divided by 1 plus 6e tau s and then s cubed 7s squared plus 6s. Something like this. You can work it out even more, but we'll see that instantly we are in trouble. We have an exponential term in the numerator part and also in the denominator part, so it's going to cause some problems. But instead of looking at this as I've written down, I can just look at it more generally like this, which is basically the same. But now, since the stability for 1 plus k times ds is this, if you look for a division by 0, this is the equation that pops up. And if we plug in j omega, we get basically this. And we've worked out and established the fact that the gain of this should be equal to 1, and then the argument of c should be minus 180 degrees. So this is our stability condition. Now, of course, we have to work it out from scratch because we don't have really that thing here. But if we have e to the power of minus tau s gs equals 0, it will be still a division by 0. And then we can see that if I plug in s equals j omega for this, I'll get this equals 0. And again, we have a minus 1 condition here. And if I convert it into polar coordinates, it is 1 and minus 180 degrees. Now, we've already covered this. If you take the absolute value of this is 1. You can use the cosine plus j sine omega tau, or even the negative version here, is you can see that the squares sum and the square root of that gives you 1 basically. The gain here of this is 1. So therefore, if you write down the gain condition first, if this should be equal to 1, this has no effect on that. Therefore, at a certain frequency, the gain of this should be equal to 1. So that's one part again. But now, we need to look at the argument of this, because that should be minus 180 degrees. So the argument of this, and I've written down that basically we have a complex number here, you can see that. And this part here is basically the argument. So what I'm trying to say is that the argument of ej theta or minus theta is basically this. So if that's okay, then we can look at the argument of e to the power of tau omega d omega, which would be the sum of the arguments of this and basically g omega. Now, if this is minus tau omega plus the argument d omega, and this should be minus 180 degrees, this will basically help us in determining that. So we can look this up for a certain frequency, and for the same frequency, we will have a negative phase effect here, which is expected because we are adding a delay. But you can see that if we use a p-type controller, if we try to design a p-type controller using the frequency domain, we most of the time, or we have to use the argument, look up for minus 180 degrees, come up with a gain, and use that gain in order to calculate the p-type controller. But in this case, it's reversed. We are looking for a gain that is equal to 1. At that frequency, we'll look for the argument of the system, and then we can determine what the amount of delay is that will basically turn the system into a marginally stable system. So therefore, we have to work out what basically omega is. And here we have the system itself. Basically, we're searching for omega. At which frequency is this equal to 1? Well, we have to plug it in and work our way out. Now, let me see if I did it really. Well, I've used the body plot in this case. Maybe your art provided a body plot. Otherwise, it's becoming a bit of a trouble in numerical thing here. You have to solve using the trigonometric identities. And, well, for this session, we don't really have time for that. So, let's therefore look for this gain condition here. This is basically 6 divided by 1, what was it again? So 6 omega minus omega cubed j minus 7 omega squared. So we're looking basically at this. So we can maybe solve it. So if this is 6, then this should be 6. The square of this, maybe 36, plus 49 omega squared. Now, due to this 6 omega here, it's not really that easy. It'll pop out a 4-order polynomial that we have to solve. Therefore, if such a case occurs, you'll basically be provided with a 4-order, let's say, solution, or it's a simple one, you can solve it. For example, if you don't have 6 omega, you're basically reducing it down to a second-order equation. So yeah, that could be a thing. But we have to somehow solve this in order to get the frequency out of it. Now, I'm going to just write down the frequency. It seems to be equal to 0.78 and 324. So if you have the body plot, you can just look it up. If you have the table, maybe you can use that table in order to come up with this value, or you have to somehow solve this polynomial. So once you have that, it's basically easy. You have to plug it in here. So minus tau, and then 0.78324, and then plus the argument of that, and equals minus 180 degrees. But you can't really do this because you have degrees here, but this is radians per second times second, so it's radians. So therefore you have to convert it into degrees, or you can convert the right sides to radians. So this would be then 180 divided by, let's use pi, so I have to use this, plus the argument. So the argument at that frequency is roughly minus 135.5, basically. So there we go. And this whole thing here corresponds to minus 44.4933. And from this point on, you will just get rid of the negative values and then just calculate what the amount of delay is. And that delay seems to be equal to 0.99 seconds. So roughly 1 second of delay can be added to the system, and it will become marginally stable. You can add less delay in order to have a stable closed-loop system. And I would say that it's basically pretty much the same as the p-type controller. The only difference is that we're not searching for a certain phase value, we're searching for the gain condition that should be equal to 1, because you cannot alter the gain of the system, so the system should be right on equal to 1, the gain of the system. And if that's the case, you can just look it up. What is the phase angle of this system? So how much can I add to the system to get this negative 180 degrees? And then that difference will give you the delay value that can be added to the system. So that's basically our first question.